Yeah, so hi all, very good evening. First of all, can you hear me and is the screen visible?
Yes, sir.
Okay, yeah, great, thanks. So, yeah, once again, very good evening and welcome back to the 12th week and the final week of the TA live sessions for Artificial Intelligence Search Methods for Problem Solving. And this week we'll be discussing some questions related to week 12, and towards the end I'll get back to the confusion that had arisen in the backward chaining problem from the last week. So yeah, without further ado, let's get started for this week's questions. Yeah, so the first question is related to a cryptarithmetic puzzle. And before going into the question, I'll first explain what this is. So we are told that cryptarithmetic puzzle is an arithmetic problem in which the numerals have been replaced by letters. That is, each numeral has a distinct letter assigned to it, and each letter stands for a unique numeral. Right? So suppose A will have 1 assigned to it, or B will have 3 assigned to it, so on and so forth. What this assignment is that we will see later on. So every number begins with a non-zero numeral. Okay, so we assign numbers from 1, 2, and 3, and so on. And the task is to find out what each letter stands for such that the arithmetic problem has a solution. There may be no solutions or one solutions or more than one solutions. And yeah, this is basically the premise. And before moving on to the questions, let me actually give you a simpler cryptarithmetic puzzle first. So suppose we have something like this. So, what do you think could be a solution to this particular cryptarithmetic puzzle or problem? So, have you understood the premise?
No.
Okay, so let me explain with this small problem. So, we have to basically assign numbers to these alphabets such that this equation becomes true. Okay, so suppose we assign A as 2. Okay, so what do we have here? 2 plus 2 equals to, it should be 4, but here we have CD, which means there should be 2 digits and they should be 2 different digits. So clearly 2 is not a proper assignment for this particular problem because that doesn't solve our problem, right? So we basically have to find an appropriate assignment of numbers for these alphabets that are given in this particular problem. So what do you think could be a possible? Okay, so we have one answer in the chat. So Archana says it can be any number from 5 to 9. Okay, so that is right actually. So if we give it say 6, this will become 1 plus 2, right? And this kind of satisfies. But this is not the only solution. So 7 plus 7 as 14 could also be a possible solution. This could be as well. Right? So these could be some possible solutions to this problem. Right? We might also have a different type of problem that doesn't have any solution. Right? So we might have something like a plus a equals to xyz. Now, what do you think? Does this problem have any kind of a solution? No, that's right. Yeah, so this doesn't have any kind of a solution. So this is the kind of premise that we are talking about. Let me show you one more example. So suppose we have if plus it equals to y. So I've shown two possible solutions So what do you think? Are more solutions possible? And by the way, are these solutions correct or wrong?
Sorry, I didn't get it. Can you explain like the previous question that A plus A is equals to C plus D1?
Okay, I'll show the premise once more. So we are given a cryptarithmetic puzzle. Okay, so basically you can say that this alphabets or these sequence of alphabets are basically a kind of an encryption. Okay, so these actually stand for some numbers. Okay, and this basically pose a problem. So imagine that instead of J there is a number over here, instead of A there is a number over here, instead of B there is a number over here, and we have to find such numbers such that this equation is satisfied. Okay, so if we go back to the previous problem, suppose we have an equation like A plus A equals to CD. This could have been B plus B or C plus C or whatever. Now if we assign A 6, then we see that 6 plus 6 equals to 12 is a possible solution to this problem, because if we assign A 6, we get C and D as 1 and 2 respectively. So we have some assignment like A, B, C, D, so on and so forth, where A is 6, C is 1, D is 2, and we don't know anything about B, so we don't have to worry about it, and the other alphabets for that matter. Similarly, there could be another possible solution. We could have assigned 7. In that case, it would be 1 and 4, and so on and so forth. Whereas in this particular equation or problem, no matter what we assign to A, we are never going to get 3 digits on the right hand side, right? So this particular problem has no solution. So we saw one example where there were multiple solutions. We saw one example there were no solutions. I'm showing one.
Okay, okay, got it.
Yeah. So here's one more example where we have two solutions are given over here, and we have to say whether there are more solutions possible. Yeah. So if you have a doubt, we can discuss that towards the end of the session. Yeah. Yeah. So as Bhavya said, there can be many solutions to this one also. So suppose we had an 8 over here instead of 9, and let's keep this as 2 itself. We will have, that is one more solution, right? So there can be many more solutions. So I hope you get the premise. So let's come back to our question. So here the question or cryptarithmetic puzzle that is given to us is jab plus jab equals to good. So does this puzzle have a unique solution? What do you think? And if there is one, then what is it? Okay, so some people say that there is no solution. Think about it. Can three two-digit numbers? Yeah, okay. So some of you have said that there is no unique solution. Okay, so what is, let's just take one solution at a time. So what do you think is one possible solution? 723. Okay, let's see 723. So we have jab plus jab equals to good, and one suggestion is 723. And what would the sum be in that case? 1446. So that fits the problem, right? So J has an assignment 7, A is 2, B is 3, G is 1, O is 4, and D is 6, right? So this is one possible solution. Yeah, that's right. So we saw that this does not have a unique solution because we can get more solutions just by interchanging one assignment in the alphabets of JAB. So I'll show you an example. So suppose we had 732 instead, or let's say 832. That would work too, right? So we see that there can be multiple solutions. So we have answered this, and I hope there's no confusion about this. So the next question that we go to is the value for the letter G unique for the above puzzle? What do you think? Okay, so a number of you say that is yes, and that is in fact true because no matter what arrangement we make, the first letter, the G, will always come out to be 1. So I'll just show you an example. Yeah. So here we have the three solutions listed for this particular problem. We already discussed 723 and 832. One more could be 943. And in all these cases, G has only one assignment, which is 1. So that answers our question. Any doubt about this? Okay. Any doubt about this particular question? Okay, that's great. This one is pretty straightforward, and so week 12 is pretty easy compared to the earlier weeks of the course. So yeah, you can aim for this week to be one of the high scoring weeks for your assignment evaluations. Okay, so here's the third question related to the same premise. So we still have jab plus jab equals to good, and is more than one value possible for j? I think we already discussed this question in a way. Yeah, so we just saw that j could take 7 or 8 or 9. So of course, more than one value is possible for the letter j. Coming to the fourth question, so what can you say about the value of the letter d? Which of these options do you think will be correct? Okay, even. Okay, someone says that it can be either even or odd. Okay, someone says that it can be an even number or 0. So would you like to explain your thought process behind it? Why do you think it would be even or odd or 0? Or,
Because b plus b always same number summation become even and also become if more 5 or it's b equal to 5 then it will be 0.
okay, yeah, that is true. Uh, but here we are told that in the premise we are told that uh, we are not going to assign the number 0 to any of the uh, alphabets. So let's keep out the question of let's keep out one of the assignments that gives 0 to any one of the alphabets. So other than that, your logic is pretty correct because we have some of same numbers over here. So irrespective of whether b is odd or even, d will always be even, right? So this is true. So the correct answer would be C. Yeah,
So, but it is marked B as the correct answer.
yeah. It only B can be the only so D can only be an even number. That is the correct answer.
Okay.
Yeah. So someone had asked me to share this slide once. So yeah, here you go. You can have a look at it. Okay, let's move on to the next question. Okay, what can we say about the letter O now? B. Okay, even number. Yeah, precisely. So just like the previous question, the same logic will follow. We are adding up uh, A two times, and up before that we are adding B two times. Yeah, so triple E 204 502 plus 502. It could have been possible if we would have allowed 0 to be assigned to any particular alphabet, but the premise, the question states that we will avoid the situation where 0 could be assigned to any of the alphabets. So yeah, if the question had allowed that, this could have been a possible solution. Okay, yeah. So just like we saw, so O can also be only an even number. Okay, so pretty convincing.
Hello, sir.
Yeah,
Sir, sir, it also can be odd if we choose a B just like a 6. When one carry out, we put A as a 7, suppose. So 7 plus 7, 14 plus 1, 5. Okay, and then one carry for J. J must be suppose 7. 7 plus 7, 14 plus 1, 15. So it
okay.
also can be 5.
Okay, so can you suggest one number for jab that you are saying?
776.
776. Oh, okay, that is not possible because you
Sorry,
are,
sorry, sir. Yes, yes, yes.
yeah, we
I
can't
understood.
assign number to two a same number to two different alphabets. Yeah, so that is out of the
Okay,
question. Yeah,
okay.
okay. So yeah, coming back to the next set of questions. So the next few set of questions will be based on the concept of uh, arc consistency. So here you are given a CSP with three variables x, y, and z, where the domain of each of these x, y, and z is 3, 4, 5, 6 that is given to you. And there are two constraints that are given to you. The first is between the variables x and y, where x has to be less than y. This is the first constraint. And the second constraint is between variables y and z, where y has to be less than z. And we are asked what would the domains be after the network is made arc consistent. Okay, so first of all, do you remember what is arc consistency? Would anyone like to share? Okay, so what do you mean by continuous? Can you elaborate a bit? Okay, let's revisit the lectures that professor used in his slides and let's see when is arc consistency true. So first of all, we form a constraint graph. Okay, uh, then we connect each element of from each of the domain of the variable to uh, the way to sorry we connect each of the element from the domain to another element from the other variables domain, which are connected by a particular relation or a constraint, and then we say that variable x is test to be arc consistent with respect to variable y. If for every value of a belonging to that domain, there is a variable b belonging to dy. Okay, and this is the procedure for making the uh, two variables are consistent with respect to each other. So let's try to solve it, the problem that is given to us, and hopefully we'll arrive at a answer. So let's start with the problem that is given to us. So we have three variables. Okay, so let us denote the domain for each of these variables through these diagrams. Okay, and each of them has 3, 4, 5, 6 to begin with. Okay, now what were the constraints given to us? X has to be less than y, and y has to be less than z. Okay, so let's just check quickly. Yeah, these were the constraints given to us. Now, given this initial condition, what do you think will be the edges between, let's say, dx and dy's for to begin with? Let's choose a different color for that. What will to what elements among 3, 4, 5, 6 from dy will this value from 3 from dx be connected to?
3 to 4, 4 to 5, 5 to 6.
Yeah, that is right, because the constraint between x and y is that x should be less than y, and we see that 3 is less than 4, so 3 is connected to 4, 3 is less than 5, so 3 is connected to 5, and 3 is less than 6, so 3 is connected to 6. Similarly for 4, 4 is connected to 5,
5 and 6.
and 5 is connected to 6, and 6 is not
Only
connected to,
6.
no, 6, it should be a strict
Yes.
less condition, so 6 will not be connected to any element. Okay, we are not given x less than equal to, we're only given less than, so 6 will not be connected to any other element. Okay, now between y and z, the same will repeat, right? Because the constraint is same, y should be less than z, so 3 will be connected to 4, 5 and 6, 4 will be connected to 5 and 6, and 5 will be connected to 6. Now we will use the revise method to identify the elements that are not arc consistent, and we will gradually remove them so that our whole network becomes arc consistent. So what will be our first step in that direction? What do you think? So given the definition of arc consistency that we just discussed a few moments ago, what do you think our next step would be?
6 will be deleted from dx.
Yeah, that's right. Thanks for the answer. So if we go back to the arc consistency problem, so we a variable belonging to dx, for every variable belonging to dx, there must be a variable in dy such that they are following that constraint or that relation, right? And here we see that 6 is not connected to any element in dy, so we will mark this for cutting down. Okay, so this is the first cycle of our arc consistency problem, and for the first thing that we do is revise and what it does is it deletes 6 from dx. Okay, and what would be the what would the next step be? Immediate next step, what do you think? Anyone? Remove 3 from dc. Okay, okay, let us revisit the algorithm and let's see whether, okay, so here is the arc consistent networks, and how do we achieve that? We, for each edge x comma y in the constraint graph, we first call revise x comma y, and then we call revise y comma x. This is the AC1 algorithm. So we start with the constraint CSP problem. In the constraint graph for each edge xy, we do revise xy and then revise yx. So here what will happen, we will first remove 3 from dy, right? Do you agree with me?
Yes, sir.
Yeah, great. So we do revise y comma x, and since 3 is not connected, 3 from dy is not connected to any element in dx, this is removed, and then we will do revise y comma z this way, right? And then 6 will be removed. Do you agree with me?
So once explain again.
Okay, let me erase all of this and start from the beginning so that there is no confusion. So you understood the discussion till the point where we had formed this constraint graph, right? There's no doubt in that.
Yes, sir.
Okay,
No, sir.
okay. So in order to make this constraint graph are consistent, what we have to do is we have to remove all the elements from the domains that are causing this to be not arc consistent. Okay, and the definition for arc consistency was that for every element in a particular domain, let's say the first element, there should be some element in the other domain that is connected to that it is connected to via that constraint, right? So for example, for 3 is less than 4, so this is connected to 4 via this constraint. 3 is also connected to 5 and 3 is connected to 6. Similarly, 4 is also connected to some element in dy, 5 is connected to some element in dy, but 6 is not connected to any element dy, right? So this is the culprit. So we will mark this for removal when we do the first step, that is revise x comma y. So the first step would be x comma y, okay, and we will remove 6. The second step would be to revise in the opposite direction. So basically now we will look at whether there is any element in dy that is not connected to any element in dx, right? So we see that 4 is connected to some element in dx, 5 is connected to some element in dx, 6 is connected to some element in dx, but 3 is not connected to any element in dx. So we will mark 3 for removal again. Okay, the next step would be to do revise y comma z, and here we will see that 4 is connected to some element in 5, 5 is connected to some element in 6, 6 is not connected to any element in dz, right? So again 6 is the culprit here. We will remove 6, and next we will do again in the opposite direction. Right, so 4 is connected to some element in dy, 5 is connected to some element in dy, 6 is connected to some element in dy, but 3 is not connected to any element, so we'll mark 3. So these 4 steps consist of the first cycle. Okay, and once we have found out that what all elements each of these revised steps remove, we will remove them at the end of the cycle, not in between the cycle. Okay, so suppose, for example, suppose we identify in this step, the first step, that 6 has to be removed. We will mark 6 for removal, but we will remove 6 only at the end. And what will that leave us with? A new reformed constraint graph that will have 3, 4, 5 in dx, right? 6 will be removed. In dy, only 4 and 5 will remain. And in dz, 3 is removed, so 4, 5, 6 will remain. Okay, is it clear until this point?
Yes, sir.
Okay, so Balakrishna, I suppose your query is answered by the fact that we are removing the elements at the end of the cycle, right? So I hope that answers your query. So now what we'll do is we'll form the edges again. So let's do that. So 3 will be connected to 4, 3 will be connected to 5, 4 will be connected to 5, 5 will not be connected to anything. 4 will be connected to 5 and 6, and 5 will be connected to 6. Right? So is this graph okay? Do you agree with me? Okay, great. Again, we will repeat the same process. Okay, we'll identify which of these elements to remove. So 3 from dx, so first we will do revise x comma y, right? So we'll first look at which of these elements from dx should be removed. So
5 should be removed.
yeah, go ahead. Okay, so you were saying 5 should be removed. Okay. Yeah,
Yeah, sir, 5 should be removed.
yeah, that's true. So 5 will be removed. So let's mark 5 for that. So
And from y to x, nothing will be removed.
yeah, that's correct.
The DZ 4 should be removed.
Yeah, okay, so I'm not writing the rest of the steps. You can follow that. So from doing revise y to z, y to x,
From z to y, we will remove 4.
yeah, that's right. So from while doing revise y to x, nothing will be removed. While doing revise y to z, nothing will be removed. While doing revise z to y, 4 will be removed. Okay, so
So the final answer will be 4.
sorry. Please repeat. I couldn't hear you properly. Okay, let's proceed. And if you have any doubt, okay, why remove 4? Okay, so when we are doing revise z comma y, 4 is not connected to any element in y, right? This does not have any edge connected to any of the elements in dy. That's why we are removing 4. Okay, so once we do this, let's form one more graph after cycle 2. So this was basically cycle 2. Okay, so let me just write it for the sake of completeness. Okay, now we will form our dx dy dz again. Sorry for that. So dx will now contain 3 and 4 because 5 has been removed. Dy will contain 4 and 5 because nothing was removed from dy. And dz will contain 5 and 6. Right? And if we connect the edges, 3 will be connected to 4 and 5. 4 will be connected to 5. Here 4 will be connected to 5 and 6. And 5 will be connected to 6. Now what can we say about this particular graph?
No one can be removed.
Yeah, that's right.
Are consistent.
Yeah, that's right.
Nothing will be removed.
Yeah, that's right. So now we have reached a state where none of the elements will be removed because we have arrived at an R consistent state, right? So this forms our solution, and let's go back to the question what it asked for. So we drew a matching diagram. Okay, we already saw that, and the question asks what would be the domains after the network is made R consistent. We already saw dx would be 3 4, dy would be 4 5, and dz would be 5 6. Let's just see the questions. So the question basically asks the same thing. The value of dx after the network would be 3 4, dy would be 4 5, and dz would be 5 6. Okay, so any confusion about this particular set of questions based on CSP?
No, sir.
Okay, that's great. So that kind of concludes the questions from week 12. So I'll quickly go back to the week 11 question that had created a doubt. So this was the question. I'll just briefly repeat the question. So we had a set of rules uh, in the knowledge base. Basically, double vaccinated variable implies candidate and so on and so forth. And we had a set of facts in the knowledge base. And we were asked if the goal is can visit, then which of these we have to be basically had to say the number of instances of each of these rules in the search tree, right? And the answer I had given last week was 1110, which I thought about, and thanks to the attendees for pointing that out, and I agree with the fact that these should have been a part of this particular search tree, although in the answer that was given in the previous year's assignment, T was not a part of the search tree, so I'm not sure why it wasn't. As per my understanding, it should have been, so that's what I'm showing you guys. But yeah, it's better if some of you can also get the clarification from some of your friends, maybe they have, if they are also confused with the same question. As per my understanding, this rule D should have been there. So this would have been something like okay, rule D had the following preconditions, right? Not vaccinated, fully isolated, and gets tested. So I'll quickly write that. So this would have been rule D. Which would have formed another set of sub goals. This would have been not vaccinated, and this is all and, right? Because these are all connected via and, if you remember. This would have been not vaccinated variable X. This would have been fully tested or fully isolated, not tested, fully isolated. And this would have been gets tested. So these are all sub goals, and this not vaccinated would have some more solution given the fact that Anisa and Ameya were not vaccinated. So here would have Anisa not vaccinated, and here we would have Ameya not vaccinated. But these two, fully isolated and gets tested, would not have any solutions for these sub goals because there is no fact or rule that supports further on, right? So the final answer would become 1111, 4 ones basically, because all the 4 rules are present in the search tree. So this is as per my understanding the answer, and thanks to the attendees who had pointed this out to me in the previous week's live session. Yeah, so yeah, your Dream 11, yeah, you had a question. So suppose P implies negation of Q is one role in the knowledge base. Okay, so let's write this down. P implies negation of Q. Okay, and What is this? What do you mean by this arrow? Okay, Q implies negation of R. Okay. Q implies negation of R. Okay. And
So
we
are
have,
you using the Jamboard? Excuse me.
oh yeah, sorry. Thanks for pointing that out. And we are given not Q. Then will we add Q implies negative I in our backward reasoning tree? Depends on what goal you have. So what goal you have to satisfy? Okay, so negation Q is the goal that you have to satisfy. Okay. So this is the goal. Okay, so these are the two rules. Okay, rule 1, rule 2. This is the goal. So rule 1 will definitely be there because this gives us a negation of Q in the right hand side of the rule, and this would create a subgoal which is P. So if P is present in your knowledge base, we can say that the solution exists. Okay. This rule 2 would not be a part of this tree because this gives us the right hand side of this rule is negation of R, right, which is not our goal or any of the sub goals present in the search tree. Yeah, I don't think rule 2 will be added. Yeah, so I hope that answers your query. Okay, so with that said, this brings us to an end of the questions to be discussed for this week. And before concluding, I would like to wish you all the best for your exams if you are appearing for them, or all the best for whatever you would like to pursue later on here on after this
Thank
course. So
you, sir.
yeah, yeah, thanks everyone for attending. And yeah, Gyanesh, so if you check the problem solving session column in the Swayam portal, you will find a link to a sheet, and that sheet has the links to all the previous week's problem sessions recorded and uploaded on YouTube.
Thank you, sir.
Yeah, thanks a lot for attending. So Dream 11, today's video will be uploaded. I'll try to upload it within 1 or 2 hours after the session concludes because that it takes that much time to process the video. Uh, Okay, regarding hall ticket and all, I'm sorry, I am not aware of those logistics. So that is if it's better if you ask those questions in the discussion forum. Yeah, so
So,
yeah, go ahead.
in our consistency problem, if there are two elements in one set, then how to solve those problems? Sir?
If there are two elements in one set, do you mean two elements in one domain?
Sir.
Okay, yeah, so you will proceed in a similar way. So
It violates the set property.
what uh, do you mean to say that two elements of the same kind? Is that what you're asking?
Yes, sir.
Oh no,
Three.
that can't be true, right? You can't have the same element twice. So you'll have an element only once.
Set property is every element is unique.
Yeah, that's right. That's right.
So once I want to ask you one question. So once if you solve, I'll be great, sir.
Okay, I'm not sure I'll be able to solve it, but okay. Oh, for which question is this?
If there are 3, 4, 5, 6 in dx
Okay.
and dy dz,
Okay.
3, 5 are connected.
Okay. Let me draw it. Okay, that will be
Yes,
better
sir.
that way. So 3, 4, 5, 6 in all three, right?
Sir.
Sorry for that. Yes, then 3 is connected to
3, 5, sir.
5. Okay.
4, 6.
Okay.
3, in DY 3, 5.
Okay.
4, 6.
Okay. As is the setting.
That's it, sir.
Okay.
Yes, sir.
Okay. So yeah, so when you do revise XY, 5 and 6 are not connected, right? So these will be the candidates for removal from DX. Here, when we do revise Y to X, 3, 4 are not connected to any element in DX. And if we do Y to Z, a similar fashion, it will proceed. There's no difference as such. Okay. That fine?
Means in DX 3, 4, sir.
Okay, so in DX, 3, 4 are, so when we do revise XY, okay, 5 and 6 will be the candidates for removal, okay. When you do Y to X, 3 and 4 will be the candidates. When you do Y to Z, then 5 and 6 will be the candidates for removal. When you do Z to Y, then 3 and 4 will be the candidates for removal. Then when you complete the cycle, you'll remove the candidates and see what is remaining. Okay, so on
Okay.
and so forth, you can proceed. Okay, yeah, so yeah, another thing before we conclude the session. So one of your colleagues had requested for a question on map coloring. Very sorry for that, I couldn't include that. I have been involved with some of my work heavily this week, so I couldn't find a question to include in for this week's live session. But I'll maybe post some resource on map coloring problem or some question and some answers on the discussion forum. Maybe not today or tomorrow. So for the assignment, you'll probably have to solve it as per your understanding. But before your exam, I think 29th is the exam, right? Is it?
Yes, sir.
Okay, so before 29th, I'll try to upload some resource or some question answer on map coloring. So yeah, apologies for that. Akhil, so yeah, as I said, previously recorded sessions are already available on YouTube. You can check out the Swayam portal to find out the links. Okay, so if there are no further questions, yeah, thank you all for attending, and once again, all the very best. If you have any feedback on the live sessions, if there is any improvement needed, you can share with me. You can write to me, or you can share on the discussion forum, so that you can improve in the next iterations of the course. Yeah. Okay, then thanks everyone for attending, and yeah, let's conclude the session.
Thank you once again, sir.
Thanks a lot. Thanks for attending.